Bismillahirrahmanirrahim. Dear students, this week I plan to discuss the assignment solution, the solution of assignment number 1 with you guys. And I have seen several assignments, and I decided to discuss this one with you guys. This was the assignment of section A. Okay, let's move on. Alright, so as you guys already know that I gave different assignment problems to different different sections. So the problems of section A include problem number 1, 5, 9, 13, 18 and 22nd. So let's see the assignment solution. So for problem number 1, we have a cantilever beam with a span of 5 meters subjected to a UDL with an intensity of 10 kilonewton per meter. This is a simple problem. There is no variation in the applied loading or support condition throughout the span of the beam. So we just need to consider one portion AB, and first step is to calculate the reactions. So if I look at the reaction value, 50 kilonewton, total magnitude of load is 10 into 5, so 50 kilonewton reaction makes sense. And similarly this movement reaction, it seems okay to me. The reactions are not marked here, so one reaction will be like this. Oh, wait a minute, it should be like this. Oh, okay, anyways, this is RA. This is, no, I think I cannot write down this way, but anyways, this RA assumed in the upward direction, and similarly we have a movement, and it's not marked here, but I assume that it is considered in this direction, in counterclockwise direction. So this is MA, and MA comes out to be 125 kilonewton meter, so it seems correct. Now there is only one portion. You write down the equation for shear force and bending moment. I will not discuss all the steps. I will just move to the shear force diagram and bending moment diagram, and I will comment on that. These diagrams seem correct to me. There is 50 kilonewton coordinate here, and if we have a UDL acting on a cantilever beam, the general shape of shear force diagram is like this. So I think this diagram is correct. Similarly, the bending moment diagram, we have just one portion. Magnitude of bending moment is 125 at the support, and it is 0 at free end. So it also seems correct. One thing about the elastic curve is that this elastic curve, when we have a fixed support, there should be no rotation in the elastic curve near the support. So if I draw the elastic curve of this, I will draw somewhat like this, means 0 rotation near the support, and then if we look at the bending moment diagram, the entire bending moment diagram is negative. It means this beam is hogging. So this should be like this. The elastic curve drawn here is kind of hogging, but the rotation was started right from the support. It should not be like that. The rotation should start after some distance from the support, because this is a fixed support. Rest of the things seem okay to me. Okay, now let's move to the next problem, problem number 5. In this problem we have an overhanging beam with a moment acting at free end in a magnitude of 8 kilonewton meter. So two reactions are assumed here, RA and RB. An important point here is that sometimes when there is no applied force on the structure, students assume that the reaction should be equal to 0, but that is not the case always. If we have a cantilever beam and that beam is subjected to a movement, a reactive movement will be generated, and the value of force reaction will be equal to 0, but not in case of the beam that has hinge support and roller support, because these supports cannot generate a reactive moment. So whatever load is applied, whether it's a force or a moment, that will be resisted with the movements in the reactions in the form of forces. So just by looking at this problem, assuming the reactions to be equal to 0 is not correct. So here the reactions have been assumed to be RA and RB, and both have been assumed in the upward direction. And when we apply the conditions of equilibrium, we get RA equal to minus RB. And then by applying the sum of moment about point C, it should be, we get RB equal to 0.8 and RA equal to minus 0.8 kilonewton. So both the reactions are equal in magnitude and opposite in direction. The way normally I solve such problems is, when I get negative reaction, I change the direction of the reaction, and in later calculations I consider the reaction as positive. But the way it has been done here is that the direction of the reaction is kept as it is, like in the upward direction, and the sign is carried forward. So this is another way of doing it. If you guys want to do it this way, this is also fine. But I personally prefer changing the direction of the reaction and then forgetting about the sign that I have obtained previously. So I just take it as positive. But anyways, there are two portions, portion AB and portion BC. Let me see the diagrams for this case. 0.8 kilonewton acting in the downward direction, and then 0.8 acting in the upward direction. There is no force acting, so a 0 degree shear force diagram. So this shear force diagram seems correct to me. And similarly, the bending moment diagram seems correct. So I think these two diagrams are correct. And as far as the elastic curve is concerned, there is one precaution regarding elastic curve, that elastic curve must always pass through the support. So here it is drawn as hogging, which is correct because the entire bending moment diagram is negative. So the entire beam will hog, but while hogging, it will not leave the support. So the elastic curve will be something like this, right? It will still pass through the support. All right, so now let's move to the next problem, problem number 9. In this case, we have a simply supported beam and it is subjected to two moments. Both the moments are equal in magnitude and opposite in direction, so they balance each other out. So I guess that the reaction should be equal to 0 in this case. The procedure is shown here. RA is minus RB, and then RB comes out to be 0. Similarly, RA is equal to 0. We can divide the beam into portions depending upon the location of the variation in the applied loading. So two portions are there, but as there are 0 reactions, so the shear force is 0, bending moment is 0, and similarly the elastic curve, like the deformed and undeformed shape, both the shapes are same. So this problem is also correctly solved here. Then we have problem number 13. It has an overhanging part and there is a point load acting at the center of the simple span. RA is equal to -10 minus RB, and then by applying the condition of movement, we get RA equal to RB. Both are 5 kilonewton. So if I look at this problem, if I look at this span AB, it is symmetrical. No load is acting on the overhang side. So having two reactions, 5 kilonewton here and 5 kilonewton here, it's better to mark the reactions on the diagrams with the direction. So RA, RB, both are equal, and that seems okay. Then the portions, so there should be 3 portions, I would say, AD, DB and BC. So for all the portions, the shear force and bending moment values have been calculated, and RA, RB 5, minus 5, and this 25. Okay, so these shear force and bending moment diagrams also seem okay. In the part where the shear force and bending moment is 0, you don't have to do this, like this hatching. If you want, you can do that, but it's not required. And then the elastic curve. Although in this part of the beam the bending moment is 0, but still the beam will, like beam is there, it will deform. So in this part the beam is sagging and it will pass through the support. And another important thing about the elastic curve is that there should be no sharp bend in the elastic curve unless there is an internal hinge present in the member. We have not discussed internal hinge yet. So in any problem that we have solved till this point, there will never be a sharp bend in the elastic curve. So the same elastic curve will just continue. It's up to point C. And rest of the solution seems okay. Next is problem number 18. We have a cantilever beam and a point moment is acting at point B. The magnitude of the moment is not given, it is just labeled as M. So in this case there will be no vertical reaction, as I discussed earlier that this is a fixed support. So whatever moment is applied here, reactive moment can be generated here, and no vertical reaction will be generated. Span is L, so we can just simply apply the conditions of equilibrium. We will get MA equal to MB, and that can be taken as M. We just need to consider one portion, and for that one portion the value of bending moment and shear force are calculated. Shear force is 0, bending moment is minus M, so that's fine. It's 125. I think this is just a typo, so this is not 125, this is M. And bending moment diagram is negative M, this is fine. Shear force is 0, and for this beam, if the entire bending moment diagram is negative, then the elastic curve will be somewhat like this. It will be hogging, and you can see that I did not start rotating the beam right from the beginning because this is a fixed support, so there will be no rotation at the beginning, and after some distance the beam will hog down. This is how the elastic curve will look like. Then problem number 22. In this problem we have a simply supported beam, and in this middle portion it is subjected to a VDL. Magnitude of VDL is 5 kilonewton per meter, and the centroid of the VDL will be somewhere over here. It will be at a distance of 2 into 5 by 3 from point C, and it will be at 5 by 3 from point D. This is something that we know from basic geometry. And again, we will first of all calculate the reactions, and we will divide the beam into portions, portion AC, CD and DB. Now let me see. Okay, the reaction calculation is done here. This minus 12.5 is the magnitude of this VDL. It is obtained as 5 into 5 divided by 2. Reactions are calculated, and then the beam is divided into number of portions. I've seen this calculation. This calculation seems okay. For shear force and bending moment, yes, in this part is a bit tricky part because VDL is not on the entire span in this case. This distance AB is 3, and B up to the section is x minus 3, and then this vertical dimension of the VDL is calculated here, x minus 3. This is correct. And the resultant is calculated as 1 by 2 into x minus 3 into y. Y is x minus 3, so ultimately we get 1 by 2 into x minus 3. This calculation, just recheck this detailed calculation. I did not check that in detail. But if I come at the shear force diagram and bending moment diagram, the elastic curve is fine. Simply supported beam, load is acting in the downward direction, it will sag down. Shear force 6.41 here and 6.09 here. The question is how these 2 points should be joined. The way these points have been joined here initially, that is not correct. As the magnitude of the shear force is increasing, so the slope of shear force as the magnitude of the applied load is increasing, so the slope of shear force diagram should be increasing throughout this portion. So it should be somewhat like this. This is the increasing slope, and when you have drawn this portion, then you will calculate what is the location of this point. For that, what you will do, whatever is the equation of shear for portion CD, you will put that equal to 0, and then you will get the value of x. That will give you the location of this point, and from this point, for this point you will calculate the value of bending moment, and that will be the location of the peak and the magnitude of the peak. So that part is not rightly done here. So I suggest you guys to calculate that correctly. In another assignment, I saw that this part was like this. This part is correctly drawn here, but this portion in the bending moment diagram is not rightly drawn, because if we have a point of 0 shear here, we should draw a guideline here, and corresponding to this point we should draw the we should calculate the bending moment. So bending moment diagram will have a peak at that location, and then it will come down. So this was the review of assignment number 1 for section A, and I will upload it on the same common folder, and I strongly recommend all the students to go through the review of assignment of each section. Okay, so and what about elastic curve? I already mentioned that elastic curve is fine. Okay, so I'll just stop recording here. Thank you.